Yeah, thank you very much, and welcome our stations in London, and welcome to those on the video streams. My name is Janus, and today we talk about design patterns in Rust. And I believe we find a lot of great ideas in design patterns, and they can empower us software engineers with better communication. And also this talk is towards software engineers. I dream of a world where safe and fast software written in Rust empowers the engineers in other fields to build the chemical plants of tomorrow. So besides that, there is this motivation I have to share this nice application example with you. I think history is important, so you get some cross-references here. And I hope I sparked some thoughts, and if I did, come to me, talk to me. I'm here for talking to you guys. And last but not least, interdisciplinary collaboration becomes more and more important. And think about it, we as a Rust community, we are quite cross-disciplinary already, right? We have those guys from the embedded programming and guys from the web development. And that's often comes with different backgrounds and terminologies. However, today we will start with an introduction to what are design patterns, what are chemical plants, more in the sense of how do we represent them in a computer. And then we will talk about two very common patterns in Rust, the builder pattern and the type state pattern. And they empower us with safe and ergonomic APIs. And after that, I want to share my mixed feelings with the visitor pattern with you, but help to decompose some ideas from it. All right, what are design patterns? I searched the web and I found a nice definition on Refactoring Guru. So it is, design patterns are typical solution to common problems in software design. Each pattern is like a blueprint that you can customize to solve a particular design problem in your code. And I think customize is quite important here. They consist of like a name, short name, 2 words, 3, a problem description, a solution proposal. Normally you also find relationships to other patterns and some examples, but on this slide I want to focus on the name, a short problem description, and the solution. So you will see this slide again. And yeah, here's the first cross-reference. This idea around patterns started in 1994 with the book Design Patterns, Element of Usable Object-Oriented Software. It was published by the Gang of Four, and this was a context when C++ and classes, like early object-oriented programming was around, and also the Java world got on pace. And they had like a peak popularity around 2010, I think. And I saw some opinions in the world of in our nice internet here. Enrique, for example, says, people who think design patterns aren't that important have never maintained a software for more than 1 year. So it's a bold statement that supports this talk quite good. However, if you dig a bit deeper, there were a lot of people expressing concerns about patterns. And that is due to the fact that we have this tendency as humans to see, like, when we have a hammer, every problem becomes like a nail, right? And yeah, so remain open-minded. And for me, it's really nice to put like short words to maybe complex topics, and to remember myself when we do this to always question the common understanding. And there's a zoo of pattern around. We will just focus here on 3. I think there are probably 300 around. And sometimes it's a bit hard to see like the boundary. Some design patterns are quite small, others go in the direction of already being like a proposal for architecture of software. With this short introduction, now get ready for what is a chemical plant. So, as you might imagine in a computer, we represent it as a cyclic graph structure. And the nodes you have that are like, they are called unit operations in this flow sheet, like a reactor, a distillation column, a compressor. And you have edges that represent pipes where these mixtures of gases and liquids were brought through the plant. And here's a schematic example. It's a lot. It's of a very popular process. It's called the Haber-Bosch process for ammonia production. This is for fertilizer and keeps us all well nutritioned because it's very important for the food delivery. Yeah. However, what I want you to take home from this is that nearly every chemical plant comes with three parts. First, we have this upstream where we want to get our ingredients ready, get the right temperature of the mixture, get the right pressure. Then you have a main part. This is sometimes one reactor, like in this flow sheet here with the Haber-Bosch, and sometimes it's a cascade of reactors. And after this main reaction, you have the so-called downstream where you try to separate products from wastes and recycle back reactants. So this was very schematic. However, I reached out to BASF, who provided these nice pictures. You cannot get them so easily because you're not allowed when you go for exhibitions there to take pictures. And here, as you can see, like the plants are really big. We have like 2 humans there with yellow helmets. And yeah, that is actually an ammonia plant. And in the end of the last century, BASF was at the forefront to solve the hunger crisis, what was like the climate crisis of the last century. And now a lot of people are working on this new crisis. Okay. We will focus in this talk on one specific unit operation for our patterns, a distillation column. And all of us know it. When you maybe saw like an evaporation of wine, and then the gas has a higher purity of alcohol, and that is how you could like produce brandy. Like you heat it up, the liquid evaporated, and that is how booze is made, or was made at least for a long time. And in this distillation columns, you normally separate mixtures that have different boiling points. So the low boiling point components were extracted on the top, and the other ones on the bottom. And in the computer, we will have variables to describe this distillation column. For example, the number of stages is representing the height, and also like where are inlet positions where we put our feet in, like this distillation columns. Then there are other variables, like you can control temperature and pressure to some amount. And so now we know what is a distillation column. Let's build one, right? And that's a nice transition to the first pattern, the builder pattern, that is responsible to, when you have like a complex object, and there are a lot of coupling fields, and you want to initialize that. So that is like the problem the builder pattern solves by proposing the solution that we add a new object for this that is responsible for the construction. So we have a separation of concern here. And for our running example, we will now construct a column in a way that all these requirements we have, like you need at least 3 stages because you have a reboiler, at least 1 distillation stage and a condenser in these descriptions, and there are other requirements. And the builder pattern is very often seen in Rust because in contrast to other languages, we don't have function overloading. And so that's a nice way to go around this obstacle. So we will now start by just introducing types in Rust. And here you can see a struct with some variables that we saw before on the previous slide. What I highlighted here are derived macros, so the common one, the debug trait, default, and so on. They add functionality to our plant. In our case, the default trait is used in our distillation column builder that just popped up. And this is a structure that just contains a distillation column, and we'll build it now in this example code. And well, in our new function, we use default, and then we have like 0 stages, no feed positions, so everything is invalid. And as the next step, we need to have ways to change this. And you find it in like 2 common variants. There's one variant where you take a mutable reference. This is this ~mute self into the function, and you return this mutable reference. This allows you to use the dot to call another function afterwards. This is also quite good when your builder is big, because when you would move or copy around something, that may be not so beneficial. However, there's this other variant where the & is missing. That means we consume the variable. That means self moves into the scope of the function, and then this function is the owner, and afterwards we return self. So it's a different thing. And this variant brings one big advantage. You could return something else than self, and that is what we will see later about type conversions. And yeah, besides that, I decided for this talk to do a very, let's say, UI near error handling. So I wrote this method here, check error, which returns a result. It's highlighted again. Yeah, I think most of you know result. We have a OK type, which is empty, and a string for the error. And internally, that's not what you would do in like idiomatic Rust, but I decided here to just fill a vector with all the errors, and then you could put it out when you build a distillation column that is invalid. And at the end, we just check, is the vector empty? Then everything is OK. We return OK. And otherwise, we will join the strings with new lines and return the error. Maybe a small addition, when you want to do error checking in like a library that you provide to the outside, you should check out the create this error. And anyhow, for when you're writing a program, and well, the build method then also comes in 2 variants. You can either consume self again, and this helps to save a copy, because we can now move out this data structure of the distillation column. And the other variant would be you want to build and reuse it. This is beneficial if you want to use a builder to build many of those objects, for example. Yeah, let's see some example usage. You often find this in some Rust code. Here in the example code, we just generate a builder and use this method chaining to set up the variables, like stages 32 and so on. And then we use build and reuse first to set up this this distillation column and match if it's OK or an error. And debug print out the result in this case, because we are OK here. So we just see the variables. And in the following code, we clear the feed position, set the stages to 2 just to demonstrate, okay, there are some errors now collected during the build method. And this is like really a idea you would more do in like older language like C++ with collecting these error messages. We will see nicer ways with generics in the next part. And what you can also do, you can reduce a bit the builder plate when you don't want to start writing your own stuff. But for example, with a type builder crate, you can use macros on the let's say main struct to define your builder and the behavior. All right, so that was like the first very simple pattern. But now we will build up on this with the type state pattern. And we want to add some states to our distillation columns. And normally you face this problem that you have data, and depending on the state of this data, you may want to have different behaviors, and for the type state pattern, particular different interfaces depending on the states. And the solution here is like, now we want to extract those interfaces in separate structs or types. And we already saw a first very simple example with a two-state pattern where we have the builder as one state in construction, and as soon as we call build, we move into this other state. Like the builder is gone, and we really have like a new type here, distillation column, and it's ready for use, let's say. But it gets more interesting, you see, when there's like a more complex column, like a divided wall column. There's just a wall inside, but it helps you to separate more than two, let's say, mixtures out of this distillation. And then you could add like another builder for the divided wall column with more complex methods, and this would also have its own build method going into another state, producing a divided wall column. There are also examples, let's say, in the standard library that are quite close to type state. That is all related to how did we came to the generalization that we nowadays have with the type state pattern. And instead, we have this file open method that generates our file, and we are safe that it's opened then when it works. That's not true in C, for example. You just have a file handler, and you never know if anybody did close it or not. So we have some luxury here, some safe and ergonomic. And when it's dropped, we are out of scope. So that's happening when a variable goes out of scope. In C++, it would be the destructor, and then Rust handles the file closing for you. And this kind of idiom was called resource initialization. Resource acquisition is initialization in C++, and it's also like some kind of two-state type pattern. And there are two common implementations. We saw like with external types, we just used several structs that were moved into each other, transformed. We have the self-ergonomic API already, but we have problems with providing common code for like several states. And for this reason, what's done nowadays in Rust is we use the traits and generics to define our type states. And this allows us to have like common interfaces over all states, for example, with an implementation block. And we will now see this in the upcoming example. So we still want to model our distillation column, and here we will use 3 states first, after the building it's configured, then like I come from a background where modeling, simulation, and optimization is interesting. So you would get the data structure ready for simulation. That means generate the equation system. And you would simulate it then. And then you have a simulated distillation column which contains some results. And besides that, from each of these stages, you could have a method changing the parameters, which just moves back our distillation column in the last state, in the initial state, sorry. And yeah, here, just the types were added. So at the bottom of the boxes, you can see type state column as the name of our new struct, and then 3 different generic type parameters configured, ready for simulation, and simulated. And, well, yeah, that's a lot now, but we want to encode the states for Rust. And for this, we work with empty structs, which are zero-size types, to tell the Rust compiler about what is happening. So for each state 1. And we have a trait called column state, which is implemented for each of those structs. And this really helps to ensure that we never can go into another state when we're using column state. So that's the encoding of the states. And what you then do, in our case, we just wrap the data. We take the distillation column as data field. And when working here with the generic type parameter S, which needs to be a column state, we don't instantiate it, but to help the compiler to reason about it, it's in this phantom data marker type. So that's just a zero-size typed. And that is like the core struct for our now type state pattern. And then you can start to add transitions with different implementation blocks. So here really where the magic happens is in the upper line, impl, type state column, and then you choose the ready for simulation state, and in this implementation block you implement simulate. And I also mark the signature of simulate here because it consumes self and returns another type which is just different in the generic parameter, in this state parameter. And yeah, here we generate the return value. So it's just moving our data to another instance. And if we want to add common functionality, we can just use bounds on the traits. Here in the above line, we have impl s for all column states, and then we add the change parameters method here. And you can see the method in detail in a GitHub repository. I will share this later. Yeah, so that is the idea how you can work with it. However, this is also the good spot to thank like 2 persons. First of all, Chiara, who is organizing the Rust and C++ Dragon meetup. She gave good feedback to this slides. And the next section it was added now after my former colleague Janus gave me some feedback, and he has a background in chemical engineering. And why is it so cool? He didn't understood why this is cool for a programmer. He was like, yeah, you're sticking to the rules, but why is this cool for a programmer? And it's cool for a programmer because in your IDE, you just get the interface you currently have in the state. And this is just 2 methods in configured here. Change parameters, generate equations. And as soon as we go into the other state, one method goes away and another transition method is added. And yeah, we will also talk about iter equations later, because the other state transition would then just add methods like get me the temperature profile of the column, get me the pressure profile, and so on. Like now we can access the results because the simulation is done. And what we didn't see so far was how do we do like iterations now for two structs. What I did in the example code is I just introduced another trait, and this trait could be quite complex. Like think about the iterator trait, or look at it if you didn't do it yet. There's like one method you have to implement, and you come with so much functionality, and you can do it the same way for like subsets of states here. And this state column with equations, a trait, has to be then implemented for each state that needs to support it. I'm not 100% sure, but probably you can also reduce the boilerplate here a bit. So if one of the more experienced guys know, let me know. And yeah, with that said, now look at some example code. And in this example code, we start with a column that was in the end generated with our builder. There's a helper function, build distillation column. And then we just debug dump the content of the struct, and we use the generate equation system method and put out the equations. So that is the output on the right-hand side for the code. And yeah, then we can just continue to use this, and in the IDE, you would really only see the methods you have at the struct. Like all these let columns, they are shadowing each other, and they're changing the types of a variable. So it's always called column, but internally you have another state, and by this another interface. And as soon as we call this change parameters, we go back to the former state. And when you look at the output at the button, you can see the marker which has like this type argument with configured in it. Yeah. You can find this example code on GitHub. Here is a link for it. And yeah, before I move on, I will drink shortly. Very well, because we will revisit the type state pattern. There is, let's say, I just wrote up some example code to show you how you can start playing around with it. But there are there's a possibility to have a really type state builder, for example, and this is important if you want to have a bulletproof library. And you do some investments then at the library level. You have the safe and ergonomic for the library users. And for example, in the Ragnar client of Lucas Putz, it's used there. And here you can see a lot of generic parameters. And the interesting thing is on the lower code, it's not highlighted on this slide. Let's see. Like you have here's a unset, and here's a set. So it remembers which variables are already set, so you can only set them once, for example, in this code. However, it would be a lot of boilerplate if you store all the variables in the builder. However, there is a nightly feature used in this repository for it. That will be someday stable, I guess. Okay. Yeah, now we get to a more controversial part, and you can imagine that because you're a programmer sitting in your basement, and I was literally programming in a basement because my parents had the computer in the basement. And when you have a pizza and Coca-Cola, and then the doorbell goes, and you were like coding a game. Visitors? Mixed feelings. And we start with a slide here. The problem is already like a well-defined object structure shall support and might be extended with several algorithms. Like I tried to like condense it in one sentence, and the solution is add a second hierarchy that visits the objects to implement the algorithm for each object type. And when I put myself in your shoes now, like just imagine hearing some of you first time a visitor pattern, it will be like, what? Before that, these template slides would be probably much more understandable. And I also found some information about visitor on the internet. My own survey said, like, yeah, that's not so nice. It's the most controversial. And also, Traf came around with some studies about patterns. And most of the replies said, like, they asked people, and most of the replies to the patterns was, yeah, they're good ideas. But for the visitor pattern, it was like mixed, to say. And yeah, Jonas Kuckenberg, he will have a talk on RustNL about an operating system, and he was also thinking about applying the visitor pattern and said, like, no, normally you don't need it. And you don't need it all, but there are good ideas in it. And yeah, to close the circle, we will now bring this example from a chemical plant flow sheet and how you could extend it. Like you have this well-defined set of objects, which are distillation columns, reactors, and so on. So here you're really thinking about like types, like a class hierarchy. Like you have a unit operation and several subtypes that are different but have a generalization. And on the right-hand side, you have an extension point, and in chemical engineering, that may be provided by the manufacturer of a pump who has a model for this pump, how it behaves. And they give you a binary, a DLL, and yeah, that's what you have to work with. So you can then implement different algorithms on these objects with a visitor pattern. So that is what the visitor pattern is in the end proposing, like separation of data structure and functionality in a very complex setting. And I'm sorry, we need to get a bit more detailed here to really understand why visitor is so misunderstood. And there are this concept, static and dynamic dispatch. Many or some have heard, and double dispatch like is rarely known, I think. And both dispatch type, they resolve a function by a receiver type, like by the type of self or the this pointer in C++. And static dispatch, on the other hand, it is using really generics and defined types. At compile time, it's very efficient, and that's how you do it in Rust with generics and bounds. No new types at runtime, so the manufacturer cannot plug in some functionality. Therefore, you need dynamic dispatch, which occurs at runtime, but therefore you normally have like a table of function pointers and an indirection stored in the data structures. And in Rust, you would use a trait object, which is like putting your traits into a box with a shared pointer onto the heap and using the dyn keyword. And then you get some flexibility with unknown types. And double dispatch, well, that's what the visitor pattern is doing, and I think it's easier to explain at a diagram. And that is what actually is shown in most of the early literature, this kind of diagram. So on the left-hand side, you have a unit operation, which is visitable, and there's a function called accept. And there you take like really a dynamic object that is resolved at runtime of a flowsheet extension. And on the right-hand side, you would use a visit method with also dynamic resolvable types. that is the original proposal. You find a lot of, first thing first, that was what I did in a C++ project for optimizing chemical plants with an external simulator. And I have this mixed feeling because like you're working on this hierarchy, a type hierarchy, unit operations, but you often or nearly always have a container too with a hierarchy like trees and graphs. And so you also get traversal into this mix. So it's good to have the separation of concerns there. And yeah, sometimes, and that was what was missing in my implementation first. And to be honest, equation systems are quite similar for every unit operation. It only makes it different if like discrete decisions like the number of stages changes your equations. So in my case, the distillation column was special. Everything else could be handled in the same case. So it was a bit of an overshoot. Yeah, nonetheless, it works. What is bad is like when you stick to the pattern, you should really end up with the object hierarchy to be well defined, because when you change it later on, that is a change you don't want to do because all the visitors have to be changed then. And yeah, what I thought was coming first here on the right-hand side, normally you don't have double dispatch everywhere when you find the visitor nowadays. So often you just use types there. It is in the original proposal though, and yeah, that leads to some misunderstanding. Well, we got a bit sidetracked here. Nice history lesson. However, let's get back on track. And where is it used in the Rust ecosystem? Well, I first find it on Google in the Rust design patterns book, and they were also proposing like having the traversal separated from the object hierarchy in method prefixed with walk. And then Zerde is one example that comes to mind when visitors are used. And Zerde uses this derived macros we saw earlier. Here on the right-hand side, I just added deserialize and serialize as derived macros, and that means, okay, my struct can be stored in some file format, right? And internally, this deserializer that just gets generated in procedural macros is then forwarded to a visitor. And the visitor himself is then implemented for each file format, like JSON, RON, protobufs, or whatever you want to use. Yeah, I didn't find so much about double dispatch. It's not so common in Rust anymore. But what I found was, at least in the mid-level intermediate language package, there is a trait visitable and a trait visitor, and this could, like you as implementer could decide if you put like trait objects into something. I'm not 100% sure how the compiler guys do it, but like this is at least the same. Double dispatch ideas could be supported there. Okay. Besides that, they have also nice, let's say, rules of best practices with a super method and a visit method. The super method is just a default implementation. Yeah, and here in a compiler, you normally work on a tree structure, which is like an abstract syntax tree. Yeah. Yeah, but to summarize, in the end, we have so many topics here, algorithms and domain knowledge. It most often, because you need to have this well-defined object structure, you need to get the domain knowledge in. You have this distinguishing between object hierarchy and the container, which might be a tree or a graph. And we heard about these details. So there is so much you see inside the visitor pattern, and that is why I think there's a lot to learn. And you can also learn from things that are complex and by decomposing them for yourself, for your own use case. Yeah, so finally, we did it. We learned a bit about the Haber-Bosch process, how you could represent this in a flow sheet. And we then focused on distillation columns, which are in fact the most common separation operation in the chemical industry. And we learned about the builder and the type state pattern that are very well used in the Rust ecosystem. And yeah, we decomposed a bit of the complexities of the visitor pattern. And yeah, I promised you some cross-references. So I think in November I started a video series with a mate of mine, Jonathan Ayala. It's called Pragmatic Rust for Engineers. And then 2.5 hours of videos, you will simulate a reaction. You will visualize it. And you will, in the third video, have like this closed loop with a user interface in WebAssembly. Like you can change some sliders of variables, change the number of reactors, and you see interactively how this is changing. And if you're interested in history and how Haber-Bosch solved the hunger crisis, check out the blog post of Jonathan. So thank you very much, and I'm looking forward to discussion.